All right. All right, so these are, as I said, performance metrics. There are many metrics, right, in AI machine learning. There's specific metrics for specific tasks, like if you're doing language translation with transformers, there's something called the BLUE score, right? And it measures how good the translation is, right? So there's many of those metrics. And then we have the more common, simpler metrics for regression, which we looked at mainly the coefficient of determination, or the R square. And now for classification, we've got these metrics, okay? Right, that we've talked about: accuracy, precision, recall, F measure. So you'll get to play with these metrics for the Sci-Far 10 competition, basically. And as I said, the metric that will determine who has the best performance will be the F1 measure, okay? So last week, I went over these equations here, basically, right, of how the accuracy, the precision, the recall, the F measure are computed. Okay, so we went over that. And then, as I said, they're all coming from the confusion matrix. So today, I usually like to go over an example that kind of helps us to better understand the metrics and why they're important. Okay. So let's go over this example. So let's kind of, it has to do with a classifier at an airport for terrorism, right? So imagine if you're maybe in a government agency, and would you believe someone who claimed to create a model to identify terrorists trying to board flights with greater than 99% accuracy, right? This is what they're telling you. Hey, pay me millions of dollars and I'm going to give you a model that has 99% accuracy. They may not be lying, but the question is that metric, that value, meaningful, right? And that's what you want to understand. So usually when we look at, data sets like Sci-Far 10, MNIST, IRIS, one characteristic that they all have is that they're balanced, right? What that means is that every class usually has the same amount of samples, right? So in IRIS, we had 50 of Setosa, 50 of Virginica, 50 of Versicolor, right? So that's balance, all right? And that's the same for MNIST, Sci-Far 10. We have like 10,000 of each, or 6,000 of each, or something. Or they don't even have to be perfectly balanced. But if like one is like 8,000, the other one's like 6,000, I would consider that balanced, okay? Imbalance is when you have something like fraud detection. And fraud detection, hopefully, most bank transactions are not fraud, right? They're just basically valid transactions that took place, but there's a few in there that are fraud. So in this example, this is, let's think about it. Here's the model. So let's think of the balance of this data set. So we have about 800 million average passengers on US flights per year, right? But between 2000 and 2017, there were only 19 confirmed terrorists who boarded these flights. So think about that. If you're building a classifier that detects terrorism versus not terrorism, you're out of 800 million only. So you have in the data set 800 million of one class and 19 of the other one. Think about how imbalanced that is. Okay, but I like this example because it should help us to understand precision and recall. Okay. So for the person that claimed the 99% accuracy, basically the person, all they have to do is label every single person flying from a US airport as not a terrorist. Is that correct? Almost. It's not correct to, name them. They're not terrorists, actually. So in a sense, it is correct that 800 million are not terrorists, right? And only 19 million are. But the problem is you're going to miss these 19 people, okay? And so that's the problem. The model is accurate in detecting this, but actually the purpose of it is to detect this. Do you see that? All right, so this model achieves an astounding accuracy of 99.99% if you just do that. So this solution has nearly perfect accuracy. This problem, and this is a common problem because we are just not using the correct metric, okay? So accuracy, I think I stated at some point, is not a metric that you want to trust all the time, okay? And when you have a balanced data set, then yes, but otherwise, you have to look at other ones. So the terrorist detection task is an imbalanced classification problem. We have two classes we need to identify, terrorist and not terrorist. And the key thing is one category represents the overwhelming majority of the data points, okay? Another imbalanced classification problem occurs in disease detection when the rate of the disease in the public is very low, okay? So that's, if you want to think of it in either one of those two cases, they're similar. In both these cases, the positive class, disease or terrorist, is greatly outnumbered by the negative class. And these types of problems are examples of a fairly common case in data science when accuracy is just not a good measure for assessing the model, okay? So that's why we have other metrics like precision, recall, and the F measure, all right? So that's the idea. So intuitively, we know that finding all negative data points in the terrorist detection problem is not going to be useful. And instead, we should focus on identifying the positive cases, right? That's really what we want to do, the 19. So the metric, our intuition tells us we should maximize is known in statistics as the recall, or the ability of a model to find all the relevant cases within a data set. So let's think a little bit about what the recall was, right? So I gave this to you last week. So the recall is out of A and B, how many A's did we find? And what was A and B? It was the true class, right? The one that we're looking for. Okay, so that's really what we're looking. Out of the 19 terrorists, we want to find all 19, right? That's the recall. Okay, so it's the ability of the model to find all the relevant cases within a data set. Okay. So let me see if I can get this thing to go. You guys can see it, right? So, yeah. So if you look at this table, this is the exact same table as before, okay? This is the recall table, just like the one I showed you last week, except that I have changed some of the names to what is very familiar to you probably if you've taken a statistics class where you saw these letters with their actual names, which are like true positive, false positive, false negative, true negative. But the meaning is exactly the same, okay? They just have their proper names. Okay, so, and this thing is in the way again. Yeah, there we go. All right, so how can we find all terrorists? In this case, let us predict everyone as a terrorist and problem solve, right? We'll find them. Yep. But that's 800 million passengers, right? And so that also doesn't work. So recall will be high, right? We found them all. Out of all the 19 cases, we found all 19. So we got almost 100% recall. What's the problem with that? Our precision will be terrible. Do you guys see that? Does that make sense? And so this is, hopefully this makes sense. Now, I'm not saying that you should never use precision and recall. In fact, there can be some situations where your objective is justifying, to use precision or recall, right? So I had one situation once where what they wanted was to find cases, not all cases, just enough cases, right? And so I had to select, okay, maybe I need recall or precision here. And, so that's the idea. So the problem in this case of recall, when we increase the recall, we decrease precision. Again, we intuitively know that a model that labels 100% of passengers as terrorists is probably not useful because we would then have to ban every single person from flying, and that also does not work. Okay, this approach would suffer from low precision or the ability of a classification model to identify only the relevant data points. Okay, So here I have written the recall function just in terms of true positives, true negatives, but it's the exact same equation that you saw before. All right, so here we have basically for recall, we have the if we think, let's tie it back to this, right? So recall was A and B. So that's the true out of all the true cases, right? A and B. So out of all the true cases, which you can see, these are the actual is the true cases. So it would be true positive and false negative, right? Do you see this? Do you see my mouse? Yeah, these two, right? Does that make sense, guys? Okay, so that's going to be out of the true positive and the false negatives. And then, so that's the denominator. And the interpretation of this is terrorist correctly identified, and then terrorist correctly identified plus terrorists incorrectly labeled as not terrorists. Okay, so the model missed them, but they were actually that condition. And so that is the real. That's recall. Okay, make sense? All right. So how can we find all the terrorists? In this case, let us predict everyone as a terrorist and problem solve. Did I just say this? I feel like I said that already. I did, right? Yeah. So, all right. So we had covered then recall. So as I'll kind of summarize it, this approach would suffer from low precision or the ability of a classification model to identify only the relevant data points. So that takes us to precision, which is this one. Again, just written in a different way, but it's the exact same equation, right? So for me, it's easier to look at the letters and then tie it to this. So let's look at precision here. Okay, so precision would be A plus C. Okay, A plus C is what? Out of the predicted, right? So this is now not all the cases that are out there, but what the model predicted itself, right? So the model predicted out of A, C, how correct are these? Okay, so this is the case that I had once where I was just looking for tweets, right? And I didn't need all the tweets in the world. I just needed tweets that were relevant. Let's say I was looking for a specific ad for some medicine that you take, right? That met these conditions. So I don't need all of them. I just needed enough. And so what I wanted was a high precision. You see that? Out of whatever this model gives me, I don't want to waste time reading through it and realize, you know what, this is not what I want. Does that make sense, guys? Okay. Try to understand this concept because you may get problems like this on the exam, right? Where I'm going to ask you, should you use, yeah, go ahead.
So recall is representation with real world value. Am I not mistaken here? So in the example, you had 800 million weren't terrorists, 19 that were, all we cared about was finding those 19
Yeah,
terrorists.
that's recall.
If we got others wrong, we only cared about those 19. Right?
Yes, you don't want to miss them, but it's a balance though. Like you can say, if you label everyone as a terrorist, then you found them, right? Because they're going to be in there. But is that really useful? No, because you have to screen 800 million people. That doesn't work, right? Probably. Do you see what I'm saying? So you gotta play with these metrics, and that's why we have the F1 measure. As you will see, it's a balance between the two.
Okay.
Okay. Good question. I mean, this is an exaggerated case, obviously, for you guys to like picture this. I mean, it's a difficult problem. Is it making sense? All right, good. So yeah, so that was precision and recall. Okay, so let's go back to precision. So I was saying this. Precision is defined as the number of true positives. So, oh yeah. So precision is, again, A and C. So out of the predicted, right? So out of the predicted. So the predicted would be true positive and false positive, correct? These are the predicted. Do you agree for this particular thing? So true positive plus false positives, the predicted. So out of the predicted, how many are actually correct? As I said, you know, if you're looking for something and you don't care that you missed a few, but what you find, it's relevant to you. Okay. So precision is defined as the number of true positives divided by the number of true positives plus the number of false positives. False positives are cases the model incorrectly labels as positive that are actually negative. In our example, individuals the model classifies as terrorists that are not. Okay. Okay, so the function you can see is true positives and true positives plus false positives. So here it's stated terrorist correctly identified. And then here, terrorists correctly identified and individuals incorrectly labeled as terrorists, because remember, is what the model says is a terrorist. Out of all of those that it says are terrorists, how many did it get right? So obviously we wouldn't want this to be a high number for the second. Got it? Questions? Okay. Yeah. All right. So now we can see that our first model, which labeled all individuals as not terrorists, wasn't very useful accuracy. Although it had near perfect accuracy, it had a precision of 0 and a recall of 0 because there were no true positives. Say we modify the model slightly and identify a single individual correctly as a terrorist. Now our precision will be 1, right? No false positives, but our recall will be very low because we will still have many false negatives. We still missed many, okay? And then we can go to the other extreme. So in other words, as we increase precision, we decrease recall and vice versa. Okay. So that's what the metrics give you, either one or the other, right? So one is for precision, one is for recall. Now, why do we have the F1 score? So the F1 score combines precision and recall to try to give you a more optimal metric. So one doesn't look at, it's not accuracy, but it's one that tries to have a good precision and a good recall mix at the same time, which is the best of both worlds. Unless, as I said, there could be some situations where you just want the highest precision possible or the highest recall possible. But otherwise, you go with F measure. Now, of course, this is a very difficult problem, and your problems hopefully wouldn't be as hard as this one, okay? You want to have more balanced data sets than this one. So in some situations, we might know that we want to maximize either recall or precision at the expense of the other metric. This is what I was saying. Here's an example of maximizing one or the other. So for example, in preliminary cancer screening of patients for follow-up examinations, we would probably want a recall near 1. What does that mean? We're going to scare some people, right? It's not fun, but what's the worst? But if you don't do that, you might miss cancer, right? And you don't want that to happen. So, for example, in preliminary cancer screening of patients for follow-up examinations, we would probably want a recall near 1. We want to find all patients who actually have cancer. And we can accept a low precision if the cost of the follow-up examination is not significant, okay? This is probably a hospital would look at this as far as the budget, right? And say, okay, if the screening is cheap, the second screening is cheap, then let's just find everyone, okay? And also from a humanitarian point of view, obviously you don't want people to die eventually, right? So the idea here is that recall is 100% and you find all the cases of cancer. Does that make sense, guys? Yeah, okay.
So if your recall is near 100%, doesn't your precision suffer?
Yes, exactly. Your precision is going to suffer. So that's why I'm saying that there's going to be a few people that are going to get, if you're like a hypochondriac, you're going to get terrified, right? If they tell you, oh, go for that second exam. Do you see what I'm saying?
I see.
Yeah. So you kind of, it's a balance between the two. There's no perfect world, right? So you balance them out somehow. If you only go with F1 measure, it's almost implicit that you missed a few, all right? So if you don't want to miss any, you gotta go with recall. Okay? Got it, guys? Any questions? So you choose the metric that you think is the more appropriate for the
How did you
situation.
get the model to train for a specific metric?
Because well, this is how you do it. So how to train for the specific metric is not maybe what the way that I would state it. I would just say, I ask all of you to build a model and I will select the one that has the highest recall.
I see, okay.
Do you see that? So Jason maybe has the highest recall, we go with his model. Why? Because that one will, maybe your model would detect 8 cancer cases, but miss 3. Jason's might detect 10 and miss 1. So there's 2 more that we were able to get, even though there's a few that we're scaring more people, possibly, right?
We're saving more lives.
But we're saving more lives, exactly, because ultimately you want to save more lives. Yes. Do you understand, Lenny?
Yes. So the precision is going to be what's the precision is.
It's a balance. So precision and so there's F1. The F1 is a metric that balances out precision and recall. We're going to look at this in a second, but I'm just trying to make it clear for you guys that we don't always need to use F1 measure. Sometimes you want to use recall or we want to use precision, depending on what it is. So precision is, again, I'll state, precision is A and C, right? Out of the predicted. So an example, I've actually done this. I was looking for tweets. How many tweets are there in the in the internet? Trillion or something, right? And I just needed examples of something that was said. Let's say toxic language. Somebody insulted someone else, right? And I needed some evidence of that. Do I need all the evidence? No, right? I just need a few that are really good. I actually want the model to only pick the best ones, the easiest ones to classify for me. So do I need 1 million of those examples with a lot? Because I have to read this, right? And so no, right? What do I want? I want maybe 100 examples, but 99 of those are on point. You see what I'm saying? That's the other example, precision, A and C. Out of the predicted 100, I'm not wasting my time. Right? Guys, do you understand? Okay, great. All right, so, and somebody asked about F measure, so we're going to go in that direction. So in some, yeah, so for example, did we say this? For example, in preliminary cancer screening of patients for follow-up examinations, we would probably want a recall near 1. We want to find all patients who actually have cancer, and we can accept a low precision if the cost of the follow-up examination is not significant. Okay. Obviously, if it's really expensive, your model needs to be tweaked a little, right? Because then patients are going to be really unhappy that when they go for the second screening, they were obligated to pay $8,000 and it wasn't necessary. Do you see how that works? All right. So, however, in cases where we want to find an optimal blend of precision and recall, we can combine the 2 metrics using what is called the F1 score. So this is why in classification, you always see the F1 as the metric being reported. So here we have the formula for it. The F1 score is called the harmonic mean of precision and recall, taking both metrics into account in the following equation. Okay, so we're going to think about, it's kind of like an average, but we'll see why it's not an average. Okay, so you can see the formula there, F1. So we use the harmonic mean instead of a simple average because it punishes extreme values. Okay, so a classifier with a precision of 1 and a recall of 0 has a simple average of 0.5. Okay, yes, right? You average 1 and 0, it gives you 0.5. But an F1 score of 0. Do you see that? So really, because you basically had a recall of 0, it's a bad model. You see that? And so this is that's what the F1 measure does, is it punishes extreme cases. Okay, it doesn't like that. So it's going to give them a low F1, basically. The F1 score gives equal weight to both measures. And then there's other metrics combining precision and recall, but the F1 score is the most commonly used. And then you can play with the weights and things like that. So if we want to create a balanced classification model with the optimal balance of recall and precision, then we try to maximize the F1 score. Again, how do we maximize towards that F1 score? All of you are training, and we're using the F1 metric. Whoever has the highest score, wins. That's what I mean by it. Does that make sense, guys? Any questions? Nope. All right. So as you know, this is really important. So I've given you this already, right? I gave this to you last week, so you already got that code. And this is what you're going to be using for the homework. Okay, and then this is just goes over that code, but I've already covered that in class. So that's it as far as where those metrics are coming from. Any questions? Nope. All right, so I do have another set of slides that we're going to cover today. Okay. Close this. So it's these two. I'll start with logistic regression. So I've written these down for you, and this is posted on Brightspace. So you can just get these PDFs from there and print them out. So let me share the screen. Okay. All right. So we're switching gears from performance metrics now to Zoom quit. Still recording, right? Okay, so hopefully it won't break it. All right, so we're switching gear from performance metrics now to just the neural networks, right? So at this point in the semester, I usually like to do like a summary or review or a contrast of the things that we've looked at. So basically, we looked at two things. We looked at regression models and then classification models, right? And you guys are building architectures, which we usually call that the inference function, right? You can always think of it as y equal wx plus b, just to remind yourself of that. But remember, it becomes a little bit more complex than that as you start building a deep neural network, okay? And we know that there's, in essence, two functions, the inference function and what's the other one called? The loss function, right? So we got two. And the fun thing about the loss function is really that there's only like two that we really have to worry about. And so that's what I'm going to talk about today, right? So kind of give you that contrast. So here, I kind of have it historically, like we had the perceptron at first, but I don't cover perceptron in this class. I cover that in the foundations class, more of a historical perspective. This is like 1940s, okay? So at Bell Labs, so it's kind of old. But it was the first neural network. But really then we have linear regression, which is a neural net. And then we have logistic regression, which is another neural net. This one is for continuous values. This is for classification. And then we have our neural nets, like deep learning and so on, right? So you can think of it that way. Let's just focus on these two though, okay? These two. So linear regression, right, is what? It's a neural net that has inputs and then you have an output, right? And the output is a continuous range, let's say from -infinity to +infinity, right? So it's a continuous valued number, okay? So this is linear regression. What does it look like? It looks like something like this, right? So you basically build a line to the data. That's the inference function, okay? All right. Classification is basically what we're studying now. And the idea there is that we are predicting classes, right? 0 or a 1, right? No longer a continuous value. If you notice, something called a logistic regression, which is a type of you can model it as a network architecture, although it's not a neural network. It's a logistic regression. It's basically, if you look, it's almost exactly the same architecture, right? You have inputs, you have an output, but the output is now constrained through an activation function, which in this case can be the sigma, which makes any value that could be from infinity to minus infinity to plus infinity into a value between 0 and 1. Okay, why 0 and 1? Because you can have two classes, 0 and 1, in a binary case. Do you guys see the architecture? Okay, here notice that we can also build a line, but now the line is flipped because it's a different purpose, right? What are we trying to do here? Classify. So we have red dots and purple dots. Okay, so it's the same line, it's just like rotated, right? And that's the objective. So we have an inference function for this space, and then we have the loss function. The loss function for regression is called, we usually denote it with J, and is MSE. We've studied this before, right? We've coded this. And remember, it looks something like that, right? So it's the predicted minus the real squared, right? So the sum of squared errors. Got it? All right. Now, for classification problems, we use a different loss function. And this is what we're going to have focus on right now, called the cross entropy. I'm going to try to give you some intuition as to how that works, okay? And hopefully you can go back to your understanding of MSE and what MSE look like, okay? So just for now, I'm only saying that J is called a cross entropy. So it's not MSE, it's a different function, okay? Okay, so here I've written down now the two cases that I'm focusing on: regression and classification. Classification can be done with what? With logistic regression, with a multi-layer perceptron, with a deep neural network, with a CNN. All of them can do classification. They just have different architectures, right? So the inference function is a little bit different, but the loss function is the same across all classification problems, because regardless of the architecture, you only care about the predicted output and the real, and you compare them. Does that make sense? Okay, so this you should already know because we've already done this in previous classes. I'm just contrasting two things right here, two losses, right? So the linear regression, we already described this, right? Why is it a curve like this? Because it's a quadratic function, right? So you take the predicted minus the real, and we call that diff. And if we square that, that looks exactly like x squared, right? And that's the quadratic function. So the samples live in this space, and we've explained that already, right? That we define this, then we have all the w's, and then if we take the derivative of that function with respect to the w, we can calculate something called the gradient. Okay, and what that gives us is it gives us a plus or minus to know how to update the weights, either positively or negative, and that way it's equivalent to this idea of taking a step, right? If I add, I take a step in this direction. If I subtract, I take a step in that direction. But ultimately, you want to arrive at an optimal point. Does that make sense? So you're taking this, that's just how it works. And astonishingly, there's only one method to train all the deep learning algorithms out there, which is this one, okay? So this is why we need TensorFlow, PyTorch. I think NumPy now has it also to calculate these derivatives for us, as every epoch and every time we're feeding it a batch, it's doing this. Okay? All right, so we had discussed that. Now, what I'm introducing that's new is this graph here. If this is the representation of MSE, right? This is then the representation of cross entropy. Okay, guys? So this is the, notice, it's like I drew it in two curves. You'll see it in a lot of places as two separate curves, but really you can think of it as one with two curves, because the fun thing about this is when you do this, one of the curves goes away. And so because one of the curves goes away, I mean, you can draw it as, becomes zero basically. Okay, but it's exactly the same thing. You have the weights here, you have a cost here, and we have an equation that basically governs, it's like the laws of physics, right? Whenever we modify that W, right, they can only change or move in these curves, basically. And these curves, just like this one, x squared defines this shape, the cross entropy equation defines these two curves, okay, in this space. And we're going to see a little bit of that in the following slide, okay? But you can draw it as one. Same idea, though. If you're here, take the derivative of it. You can go in that direction. Here, take the derivative of it, go in that direction. Ultimately, you're trying to get to the minimum. Now, don't get confused because they intersect here. Remember that one or the other will go away. So really, the lowest point is going to be down here for these curves, depending on which one you're looking at, okay? Same idea. You take the derivative of it. Remember, I wrote down here cat, dog, Virginica, versicolor, and setosa to indicate that this is for classification. This is for regression. So this is for wine quality data. This is for CIFAR 10. Okay? All right. Keep going. Now, just like for the loss functions, we have two drawings or diagrams, right? That's imagined that that's like one universe, one space for the inference function. And then we have a separate universe or space for the inference function. So this, so here I've kind of drawn this for MSE. So in linear regression, which uses the loss function MSE, which looks like this, y minus y hat squared, right? We have basically two functions and two spaces, right? So the inference is this one. Given x, we predict y. We're trying to fit a linear regression. So these are the data points, and we build that line in that space. That's the space where the data lives, and that's associated with the inference. The loss is the other thing, and basically that governs the relationship between the weights and the cost, because what you want to do is to minimize the cost. And therefore, in this curve, if you take the tangent, depending on where you are, it'll take you lower, right, to the bottom of the bowl, if you want to think of it that way. Does this make sense? So you have two functions, two spaces. Okay? All right. That was linear regression. Now let's look at logistic regression, or it could be, I wrote it for logistic regression just to keep this equation over there simple, but it can be what comes after logistic regression, multi-layer perceptron. What comes after multi-layer perceptron? Deep learning. What comes after that? CNN, and so on, right? They're all just more complex architectures, but the rest is pretty much the same, and you're still predicting classes. So here in logistic regression, we use cross entropy, another function. Basically, there are actually in coding, when you're writing this in PyTorch, there's actually two types of cross entropy, either binary cross entropy or multi-class cross entropy, right? So like CIFAR 10 is multi-class, but you can also have some cases where it's binary, like just two classes. Okay, so here, same idea. We have the inference over here, and this is the loss, right? So the inference is, for logistic, is wx plus b, which is z, and then you run it through the sigmoid so that the output value is now always 0 or, between 0 and 1. Make sense? Now, if you notice here, I drew two charts, but it's really this one, right? Because it might be easier to picture this as two things. But if you notice, one is a curve going that way, going down. The other one is a curve going up. So that's what you're going to see here, the two curves. And this is because, as I said, when you actually implement this, one of them goes away, always. And you'll see that it should become obvious in a second, okay? Now, the example I'm doing is only for binary cross entropy because it's easier to understand. I can give you some notes if you'd like to understand the multi-class, okay? But I'm not going to cover that today. All right, so here is the fun equation that we use for cross entropy. Very nice and exciting equation there. And what is it that you want to understand about this? This function that uses these logs and everything creates those curves that I showed you before, okay? Just like x2 creates that bowl in 2 dimensions, right? We understand how that works, right? We create, if you have an x2 function, the chart of it looks like that curve. Now, if we have this function, we get these curves going up or down, okay? So let's dive in a little bit deeper into this. So this is cross entropy just for the binary case, right? Remember, J denotes in machine learning the loss function. So it's actually, this is 2 things, okay? So the square is one, the thing in the rectangle is one thing, and this up here is another thing, all right? But they're the same equation. So if you look, basically we can say that the cost function has 2 forms. If y is equal to 1, then we use this one. And if y is equal to 0, we use that one. This is where I was saying that we decide which one we want to use, and each one of these creates the curve as we want it. So this here represents the real class, okay, the real label. Okay, and then based on that, we decide which one. Now, for convenience, a lot of people just write it as this equation here, one single equation. If you notice, this contains both these parts in here with one fun thing. Notice that they're being multiplied by this y or this 1 minus y. So why is this really great? It's really great because let's say that your real class is 1, right? Then what happens? This 1 here is 1. So 1 times this just gives you this function, which is the one up here. 1 minus 1 becomes what? 0. And then what do you do with this term? Get rid of it, right? And so basically you end up with either one or the other. You see that? So this is why I was saying that even though you can picture the whole thing as that, you only end up using one or the other. And then as you're choosing the W's, they only live in these curves and nowhere else. So when you're taking the derivative, it's gonna go down. Okay, and that's the function that is used for training classifiers to cross entropy. Will I require you guys to write these equations from scratch? No, of course not. We only say cross entropy, but you should know that this is how it works. Okay, tie it back to MSE, which is obvious, and then just think of it in here. So let's keep going. All right, so I'll try to finish these slides. Okay, so we are here. Okay, so this is the equation for cross entropy. For binary cross entropy, just keep in mind if it's multi-class, then we have multiple terms, okay? Surprisingly, you know, most classification is just cross entropy loss, and that's it. There may be variants of it, like a softmax cross entropy, but they're all basically the same idea, you know, and that's it. AI is actually sometimes like, we have like one thing that does everything, right? So now let's take a look at, I'm gonna drill down now into these equations, but in the diagram space, okay? So in the diagram space, now I've broken out that initial chart into the 2 parts, okay? So I have the 2 functions, this one and this one, which as you can see are this one and this one. And you should understand that where we have, you know, here we plug in the function itself, right? So really the thing that we care about is the W. Why? Because, or in the B, because these are the parameters that we are playing with, right? We're changing them. Right? And as we change them, the point is going to move in the curve, okay? In terms of the cost. So here you can see This is why this is called gradient descent, right? So it's gradients, you know, and going descending, right, in these curves. So here we have the case. So if y is equal to 1, right, the real label is 1, which we will, you know, we would have when we do the loss, right? When we do the loss, we take the real and the predicted and try to optimize it, correct? So we have them. So when y is 1, what is the objective of the model? For the predicted to also be 1, right? So that's why the curve goes down. In terms of this, the cost is going to be the lowest when this is closer to 1. If this is closer to 0, what's the cost? Well, no, not real. Well, here, if the value is 0, what does the cost look like? It's really high. Here I've written it. See this dot, 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 dot here? So let's say that you have your value here, right? In this curve, you have a really high cost. What does that mean? That's a really bad W, really bad weight. You see that? So you have a good weight here in this case. And if you notice this weight over here, dot, 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 gives you a low cost. Does this make sense, guys? So this is the diagram representation of what the equations are doing, okay? And again, this is linear regression. We use MSE. The curve thing that we here is classification, and we use cross entropy. If we look at the other extreme, the other case is when we have a real value y equals 0 for this binary problem, right? The two classes are 0 or 1. So if it's 0, then we already know that one of these cancels out, right? So if it's 0, this one cancels out, correct? And you only end up with this term, and this term then, you can see it down here, creates, or is a function that looks like that shape. And then conveniently, we use it to minimize towards 0. Why? If I choose this dot, dot, is this W here, dot, 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 what does that give me in this curve? A high cost. Very good. And if I pick this, you can see I wrote in purple here a little, this W, in this curve, what does that give me? A low cost. So that's my optimal. Now remember that once again, like before, you're doing gradient descent. So that means that whenever you choose a W in one of these curves, what do? You get that tangent, and it's going to tell you the direction to follow. Does that make sense, guys? Yeah? All right. So that's basically it as far as the loss functions, really, because there's only MSE and cross entropy. Okay? Yeah, that kind of is that. Now, the other thing in logistic regression that if you remember I did, going back to the inference function, is this, right? I had Wx plus B, which becomes Z. They call this the logit. And then this C is plugged into this function sigmoid, okay? Now, in regression, you only have Z, and that gives you a continuous value, a real valued number. So if we go over here, it gives you this infinity, right? But here, we run it through this additional function sigmoid. So this could be any value, right? But it's transformed to another scale. And these are the activation functions, okay, guys? So now let's take a look at one. So we're done with the loss, cross entropy. And now the softmax, I know we've covered, but that is the sigmoid function. Okay, it's literally an equation where the function takes in a value, which could be a continuous value, and it's e to the minus that value, right, plus 1, and that's the denominator, and then you have 1 divided by that denominator, and you get your result, okay? So what does that effectively do? It takes you from real scale to 0 or 1, between 0 or 1. And that's why we use sigmoid, because we want to predict only between 0 and 1 and nothing else, because we only have two classes, 0 and 1. Does that make sense? Softmax is like sigmoid, but remember, it adds up to 1. Okay, and we've discussed that already. Here is another chart of this example. So Wx plus B goes into Z, goes into S. And what is S is the sigmoid function. So here's the diagram of how it looks. And it's basically like that, okay? Notice the x-axis is the input and the y-axis is the output for this function. So this is what an activation function does. So if I give you a z of -3, what is going to be the result of that after running it through sigmoid? 0. Remember, you map this axis to this axis. So -3 is it lives here, it lives on another curve, right? It's the exact same idea as before, except now we have this curve. So I give you -3 and it's almost 0. What if I gave you -1 million? 0. Yeah, -1 billion. 0, right? And to infinity. If it's 0, it's 0.5. If it's 2, notice it's 1. Do you see that, how that works? These are the activation functions of which we have several. Okay? All right. Okay, so these slides end here. Remember, these are already on Brightspace. Let me check out the time. What time? All right, 6:25. I'm gonna stop the video here. We're gonna take a 10-minute break. And then I just have another set of slides that I also want to cover. And then after that, hopefully, we'll get to CNNs. Got it? All right, so let's take the 10-minute break.